So would this still stick then? So I don't know which of these is true. I don't even know if either of our models are true, but do they explain the sticking phenomenon? Do they explain how a balloon can attract a neutral object? Yeah.
So the neutrons always like adapt to their environment?
Well, neutrons don't ever do anything, but neutral surfaces can become locally charged if you bring a charged object close to it. Okay, so it's called inducing a charge. So if you bring it close, if you bring this close, because the minuses are free to move, you can induce a charge here, or you can induce a charge here. Does that sound good? Okay. Let's see which it is. Okay. Let's see which it is. What's that?
How are we able to tell?
That is a great question.
Are we gonna rub it 1,000 times?
Why would you rub it 1,000 times?
The hot's gonna make a spark?
That just seems weird.
You can tell. I'll try to make a giant spark.
You want a giant spark or you want a small spark?
Small spark of some sort.
Small sparks sound good.
Well, a giant balloon. Of course, but
So this is a simulation. Okay.
cold fat.
This is a simulation. And I love this one. Okay, I love this one. Go ahead. Because I can take my balloon and I'm going to rub it on a wool sweater. I know. It's very exciting. Very exciting. So what do you notice about my balloon right now? What do you notice about the distribution of plus and minuses of my balloon?
They're equal.
They're equal, so the balloon is neutral. True. What about the sweater?
They're equal.
Okay. Totally neutral. And what do you notice about the wall?
It's
Neutral.
It's also neutral. True? So let's see what happens when I bring my balloon. I'm going to rub it on my sweater.
You stole all the electrons.
Okay. What happened here?
You stole everything.
Okay. Did I pull the electrons off?
All but
So-
3. Take the other 3. Take the other 3 electrons.
Oh, it's because it's attracted, so it keeps doing that.
That's right. So what is the overall charge on the sweater?
Positive.
Positive. And the balloon?
Negative.
So if I let it go, which way is it going to go?
Back to each other.
Right? It's going to go that direction, right? Because there's an unbalanced force on it. If there's an unbalanced force, it's going to accelerate in that direction. Does that make sense?
Bring it to
Yes.
the wall.
So I'm excited to see what happens to the wall. Okay? Is it going to stick to the wall?
Yeah.
Okay, what if I if I pull this? Is it going to stick to the wall?
Show the charges.
It's going to stick to the wall, right? Let's stick to the wall. You want to show the charge? Let's see what happens. I'm so excited. What happened?
Pushed away all the electrons.
So it pushed away all the electrons. Is this consistent with our model?
Mm-hmm.
It is, right? Is this consistent with the original Josh hypothesis?
Yeah.
It absolutely is. Josh says, I think that when you rub that balloon with that fur, well, the chance of being here is good.
They're doing pretty good.
Okay? So that makes a lot of sense to me. You guys okay with this? So this is the model that I want you guys to have a good handle on. Is that the minuses are free to move, the pluses are locked in place. You can induce a surface charge over here, right?
Now, what if we had 2 balloons?
Okay. Okay. If we have 2 balloons, okay, what are these 2 balloons going to do to each other?
Push each other away.
Are they going to repel? Of course they're going to repel, right? Because both of them are overall negatively charged, and so therefore they're going to repel each other.
Whoa, would you look at that?
Mr. Pettit,
Yes?
if you forced them to come together, would one of the balloons pop?
I mean,
Not on the simulation. Why is it going back and forth?
because it's like,
It's getting
The
pushed
pole-
away by the
it's being repelled
negative charge,
and
but
attracted.
pulled by the shirt.
It's being attracted by the shirt while being repelled by the other balloon.
That's weird. So this is just showing the charge differences. So it's over. Both these are overall negatively charged, and the balloon and the sweater is overall positively charged. And Bob's your uncle. Does that sound good? You guys feel good about this? All right, fantastic.
So we're gonna do the simulation or we're just gonna not?
Are you gonna what?
Are we gonna do a simulation or not?
That was the simulation.
Okay,
Didn't you like it?
alright.
You don't like it.
It's alright.
I liked it.
Can we
I
make
can't believe you didn't like it. Whatever, Jacob.
Just make it spark. I just want spark.
This is a big piece of Teflon.
What is
This is a big piece of Teflon. It's weird to feel it. It's weirdly heavy. Isn't it weirdly heavy? And very smooth.
Yes.
Because, what's that? Yeah, it's weirdly heavy. Here, feel it. I don't know. And it's because Teflon, okay? Teflon is what they make like non-stick surfaces out of.
Yep.
Teflon is what they make non-stick surfaces out of.
Yep.
It wasn't a question.
I've
He's like, yes, it is.
I've been knowing this for a while.
Heavy though.
I'm in organic.
Heavy. Have you known it for a while?
I'm an intro to organic.
You're an intro to organic chemistry?
Yeah.
How's that? But that's super exciting.
That's, we did that like maybe second semester, I think it was. I mean, second quarter. Yeah, I was in second quarter.
Where's my fur?
It's on the moon.
I don't know if these balloons, I don't know if I can charge these balloons up today. They're good for usually one day. Oh, that's not too bad. Okay. Ooh, solid. Okay.
Good.
So tell me what you know about the balloons. Are they positively charged or negatively charged?
Negative.
Negatively charged. And are they both negative?
Yes.
Yeah.
Teflon.
So you can use that.
Can you hear it popping?
Yeah.
Look at this. What's up now? Look at this is so exciting. You guys aren't nearly as excited now. Mr. Cuter. So you need to open your eyes or you need to go someplace else. This is the last time I'm going to tell you. Do you understand? You may not sleep in my class. Okay? I know you're tired. I feel your pain. Don't sleep. Okay. So, obviously the Teflon can become negatively charged also. So here's a weird thing. Here's a weird thing. What happens if I go like this on this styrofoam?
Negatively charged.
Yeah.
Wow.
Now turn it around.
Is that okay?
Yes, now turn it around.
Turn it around. But if I'm using this to put electrons on here, what has to be true of this thing?
That's positively
Okay,
charged.
when I go like this, is it possible it's positive?
What? That's so sick.
I know, right? But what I like about it is it's super consistent with our model understanding of the transfer of electrons. Now let's do something weird. Okay?
Teflon.
Your Teflon fell.
Take a step. I need your desk.
You need the test. You stole the test.
Okay, are you ready? So, I'm going to put this on here.
All I know is you have to.
Okay? So I've deposited a bunch of minuses on there. Is that cool?
Mm-hmm.
Now, I'm going to bring this close. Okay? Now listen close.
What? Sick.
What on earth just happened? Did you hear it?
Put your
Yes.
finger back on.
Did you hear the actual electrons jump from there onto my finger?
Yes.
Do it again.
Now listen.
This shocking.
Yes. No. Come on up. You can do it. Yes.
Yeah, do it.
It's all you. Okay. So I'm going to bring this close, and you just touch the edge with your finger. Go ahead.
That's what
Right there.
Ah!
Okay.
Ow.
Wait. Put it back.
I have to do it again?
Yes.
Like what?
Right there.
Ow!
Big clap for Marianne. That was amazing. So, what on earth is happening in this demonstration? What on earth is happening? if we can get a sense of what's going on with this thing, this is good, yes?
I was saying you were hurting Mary Ann.
I was not even hurting Mary Ann. Mary Ann
you
is
are.
exaggerating a little bit. Why is that balloon thing still oscillating back and forth? That is, we gotta
Because
stop.
it's still,
We have to stop that. Okay. So, here's the deal.
it's hard.
We know that our balloon is negatively charged, true?
Yes.
Okay, so here's what we're gonna do. Okay, so I'm gonna charge up my styrofoam. Obviously negatively charged, true?
Yeah.
That will be
Okay,
negative.
now, here's what I'm gonna do. The pie plate is neutral.
Yes.
Drop
I'm gonna bring it close.
it, let go.
What happens to all the minuses in the pie plate? If I bring it close to this thing that's minus, what happens to the minuses?
You
Go
retract
to the
that.
other side.
They get pushed upward,
Yeah.
right?
Styrofoam.
They get pushed upward, right? They get pushed upward away from the styrofoam. If I give them someplace to go, they jump through the air onto me. Yes? But now I bring this away here, a bunch of electrons just left here, so what should be true about the pie plate?
Should be negatively
Should be
charged.
positive. It's positive.
The positive, it should be positive because of the fact that the electrons left. Does it look like it's positively charged?
Mm-hmm.
Yeah. In fact, it looks like it's super positively charged,
Whoa.
right? I mean, this is a super non-contact force. Now, I know that neutral objects, now it's positive, I'm going to touch it again, electrons jumped back from me onto here. So it's now neutral, okay? It's now neutral. It'll still attract because it's a neutral object. But what do you notice?
It's not
It's
It's
strong.
not as attractive, right? So neutral object will attract, but if it's positive and that's negative, it'll attract a ton. Is that okay with you guys? We're feeling this all right?
Right.
Okay, so. This is the fun fly stick.
What does it
It's very
do?
fun.
What does
Okay.
it do?
What is it supposed to do?
I can develop a positive charge on the top of the fun fly stick, yes?
Mm-hmm.
What
Is that
about, what about on the bottom?
No. The bottom is just neutral, because I'm holding the bottom. So the fun fly stick gives an overall positive charge. Does that make some sense?
Yes.
It looks good too, doesn't it? Like, you know, that's clearly a positive charge. Clearly a positive charge,
Yes.
okay? There's a little button on that runs a little motor in here.
Do it 1,000. Do it for a few years.
How about I come over and shock you with it? No, I'm kidding, it does not shock me. It does not shock me. Okay. Uh,
What is the molecular formula?
Do you know?
don't like it.
Okay.
So, what happened? When we rub the styrofoam plate with the fur, what happened to it?
It became negatively charged.
Yes. So, just like rubbing the balloon with the fur, okay? It became overall negatively charged. Is that fair? When I now bring the pie plate close, so the pie plate looks like this. Right?
Don't forget
Now,
styrofoam cup.
the pie plate has the little styrofoam cup on top, right? Now, that looks okay. So what happens here? Okay. If I bring this close, what happens to the minuses in the pie plate? Where do they get pushed?
Top.
So if the pie plate was plus minus to start, if the pie plate was plus minus to start, what happens when you bring it close to here? All the minuses move up here, true? Okay, all the minuses move up here. Now, here comes the cool part. When I bring my finger over close to this, a anatomically drawn to scale hand.
It has 4 fingers.
What does it see about the pie plate? Does it see a neutral pie plate or does it see a charged pie plate?
Charge.
It sees a charged pie plate, right? Because when it comes close to here, it looks like this pie plate is positive or is negatively charged, true? So what's going to happen to the minuses in the finger? The minuses in the finger all get pushed backward this way, and it leaves the front of the finger positively charged. And then, and this is the coolest part, if you get close enough, the minuses will jump.
What if we turned off the lights? We'll see a little spark.
Maybe.
Can we try?
Sure. Anthony, wake up and shut the lights off.
We'll let the lights in the back.
Jill, can you get those lights in the back?
All of them.
Yes, please.